Solving the inclined plane with friction. So now it's time to make the problem more realistic by noting that not too many surfaces are frictionless. So let's assume there is a friction force between the plane and the box and it is moving down the incline. What is the direction of the kinetic friction force? Since kinetic friction acts to oppose motion, it can be directed up the incline in the negative x direction. In order to solve for the acceleration, we'll solve the y-axis first. So in our y-axis, we have normal force minus mg cosine theta equals 0. So the normal force is equal to mg cosine theta. We'll need this for friction. Now in the x-axis, we have mg sine theta minus the force of friction equals ma. That's mg sine theta minus, now for friction we'll put in mu times the normal force equals ma. Now let's plug in our value for normal force. Now we'll divide both sides by m. And so now our A is equal to g sine theta minus mu g cosine theta. And we can also factor out the g if we'd like. And we can see here that if there is no friction, if mu was 0, we would get A equals g sine theta, just like we did before. So again, the general solution for objects sliding down an incline is A equals g times the quantity of sine theta minus mu cosine theta. It's a bit different from the result that we obtained for A when there was no friction, where A is just equal to g sine theta. A common practice in physics is to apply a limiting case to an answer and see if it gives you something that agrees with previous work. Typical examples are letting a variable equal 0 or approach infinity. Which limiting variable would you use here to validate the acceleration for an inclined plane with friction? For the inclined plane without friction, you assume mu is equal to 0. If you plug this into A is equal to g times the quantity sine theta minus mu cosine theta, you see that you get the previous result, A equals g sine theta. So it checks out with our other equation. Of course, that doesn't mean that we're right, but it's a good indicator that we're on the right track. And of course, in this case, we are right. Now, what if we were given an inclined plane at an angle with the horizontal and wanted to find what value of the coefficient of friction would allow the block to slide down with a constant velocity? Well, what we need to do is take the previous equation and set A equal to 0. So we had A is equal to g times the quantity of sine theta minus mu cosine theta. So we'll make A equal to 0. Now if we divide both sides by g, we get 0 equals sine theta minus mu cosine theta. Now we'll add mu cosine theta to both sides, and we have mu cosine theta equals sine theta. Now divide cosine theta on both sides, and you get mu equals sine theta divided by cosine theta. Sine theta over cosine theta is simply tangent theta. Let's change that problem a little and assume that the object is stationary on an inclined plane with friction, and we want to find the angle at which the object will start accelerating down the plane. We will now use static friction. We just showed that for an object sliding with a constant velocity down an incline, that mu k was equal to tan theta. The same free body diagram is used for the case of static friction. The only difference is that where Fk equals mu kn for kinetic friction, Fs is less than or equal to mu Sn for static friction. How will this modify your answer? Since we're trying to find the minimum angle at which the box will start moving, accelerating, it will be when mu s is a maximum, right before the object moves. Mu s equals tan theta. So the answer is, it's the same algebraic formula, but mu k is replaced with mu s.